Welcome to Brain Vision.
So we have a 10 kilogram crate on an incline like this, and there's an applied force pulling up the ramp of 100 newtons. We also know that the coefficient of friction is 0.4, and the initial velocity is 1.5 meters per second. And this total distance of the ramp is 5 meters. Oh, and this is 20 degrees. That's okay. So that's pretty much everything we're given. Now first we want to find the work done by gravity. And there are a couple ways to do this. I'm going to say that it's going to be the negative change in gravitational potential. And that way I can just deal with the potential and I don't have to worry about any forces or distance or anything like that. So this is going to be minus mg times delta y, so y final minus y initial, and y initial is 0, so this is just y final. So that's minus 10 times 9.8, and then the y final, well, we know the hypotenuse, so that means the height of the ramp is going to be 5 meters, the hypotenuse, times the sine of the angle theta, so 20 degrees. And this gives us 100 minus 168 joules of work. It's important that it's minus because gravity is doing negative work. The force is pointing down, but the crate is going up. And now we want to find the increase in internal energy due to friction. So that'll be, I'll call that delta E. And again, I can do a similar thing to what I did for the gravity. I can say the work due to friction is minus change in energy. And then the work due to friction, well, that's going to be the force of friction, which is mu times the normal force times the distance that it travels. And since friction is pointing in the opposite direction to the block's or the crate's motion, the work is actually going to be negative. So that means both the negatives cancel out. Now the normal force, if you haven't memorized, it's easy to know what the normal force will be for something like this, but if we just, let me draw a quick free body diagram like this. So we have gravity pointing down this way, and the normal force here. So we know that the normal force and the component of gravity that's perpendicular to the ramp or the surface that the crate's sliding on are going to sum to 0 because it's not moving in that perpendicular direction. So this will be minus mg and then cosine theta because we're going perpendicular, and that has to equal 0 because the forces are balanced. So that means the normal force is mg cosine theta. So I can plug in here, I can say mu mg cosine theta times the distance is the change in energy. Mu is 0.4. The mass is 10 kilograms. G is 9.8. We're going to take cosine of the angle 20 degrees and then multiply that by the distance, which is just 5 in this case because we're looking at the length of the ramp, not the height. And you multiply all that out and you get 184 joules. So that's the change in energy or the increase in energy due to friction. So now we want to figure out the work done by the applied force of 100 newtons. So it's just going to be the force times the distance since they're parallel to each other. So that's 100 newtons times 5 meters. comes out to 500 joules of work. And now the change in kinetic energy, that's going to be the sum of all the works that we've found. So we have the work applied, and we also had work due to friction. We also had work due to gravity. So this is going to be 500. The work due to friction, well, here we got 184 joules, but that was the change in energy. And remember, we canceled the negative. So the work due to friction is actually negative 184. And the work due to gravity is also negative, and it's 168. And this is 148 joules. So now that we know the change in kinetic energy, we can figure out the speed of the crate, because this is going to equal 1/2 m, I'm going to say v final squared minus v initial squared, which is the total work. So v initial squared we were given in the problem. I wrote it up here. It's 1.5 meters per second. So this is going to be, we're solving for v final here. So I'll say v final squared. This is going to be 2 times the work divided by the mass plus the initial velocity squared. So we'll take the square root of all this and then plug in the numbers. So we have the total work, which we found in the last part, is also the change in kinetic energy, 148, divided by the mass of 10 kilograms, and add in 1.5 squared. And this comes out to 5.64 meters per second.